Following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are two different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmayo@ybcc.edu and I'll respond as soon as I can. All right. So today we're going to wrap up section 11.5, that is 11.5 part 2. Before we go on, are there any questions from any of you? All righty, I'll take that as a no. So earlier on, we looked at a compound interest formula that looked like this. A equals P times 1 plus R divided by K all to the KT power. Then yesterday we looked at an equation that could be used for continuous compounding. A equals P times E to the RT. So the difference between these two, here you have compounding happening finitely, that is yearly, semi-annually, quarterly, monthly, daily. Whereas here, it's a continuous process. So a key word in a problem is, if it's talking about interest, is it continuous or not? And if it's a population that's growing or decaying, that's going to be continuous growth or decay as well. All right, let's take a look at an example. This says, right here in the directions, it says continuous compound interest. So that's the clue that we're going to be using this formula. An initial investment of $2,000, so that's P, earns 8% interest, that's R, which we convert into a decimal number. Compounded continuously, what will the investment be worth in 15 years? All right, so A equals $2,000 times E raised to the 0.08 times 15. As I mentioned before, we can predetermine this amount and then go from there, or we can just leave it as a product but put it inside of parentheses, which is what I'm going to do. So 2,000 second ln, which gives me e to the whatever power. So right now I've got this. Okay, then I'm going to put in 0.08 times 15. 0.08 times 15, close it up, push equals, and I get 6640.23385. Now, because this is money, even without it telling us to, we would round off to the nearest cent. Here's your decimal point. So this is the dollars, this is the dimes, this is the pennies. The 3 would round down. So we get $6,640.23. Any questions about that particular problem? All right, let's take a look at another example. It says determining previous balance. An account now contains $3,610 and has been accumulating interest at 8% annual interest compounded continuously. How much was in the account 4 years ago? Okay, again, it's continuously, so we're going to use this formula. Only now it's telling us the end amount and asking us to find the beginning amount. Let's see, it says the interest rate is 8%. So again, 0.08. How much was in the account 4 years ago? So time is 4 years. So we know the ending amount, we need to find the starting amount. So we got $3,610 equals P times E raised to the 0.08 times 4 years. Now, in this case, I am going to predetermine what 0.08 times 4 is. Let's see what that is. 0.08 times 4 is 0.32. The reason for that is because in this case, I need to isolate P. So I'm going to divide both sides by e to the 0.32 power. Okay, so P equals $3,610 divided by e to the 0.32 power. So on my calculator, 3,610 divided by e to the 0.32 power, close it up, and I get 2621.398024. This would be the nearest cent. The 8 would round up. So the starting amount would be $2,621.40. So again, this problem, it's kind of like Jeopardy. We've got the answer. What's the question? We have the final amount. What's the initial amount invested? So notice I put that number in for A and then solved for P. Any questions there? All right. Here's another problem. It says bed bugs. If not checked, the population of a colony of bed bugs will grow exponentially at a rate of 65% per week. If a colony currently has 50 bed bugs, how many will there be in 6 weeks? All right, so we're talking about a population, so it's going to be growing or decaying continuously. So we're going to use this formula. The population of a colony of bed bugs will grow exponentially at a rate of 65% per week. So the R is 65% or 0.65. The colony currently has 50 bed bugs. How many will there be in 6 weeks? So A is the unknown, and 6 weeks is the time. So 6 weeks. So here, notice the growth rate is per week, and the time is in weeks. So A equals 50 times E to the 0.65 times 6. A equals, so we've got 50 and then e to the 0.65 times 6, which is 2470.122455. So to the nearest bed bug, 2,470, because the 1 would round down. Wow. Just makes you want to go lay down in your bed, doesn't it? Okay. Any questions about that example? All right, let's take a look at another situation. This says the Big Easy. I'm not sure why, but that's the title. It says New Orleans has steadily won back some of the population it lost in the wake of Hurricane Katrina in 2005. If the current 8.2% annual increase in population remains constant, how long will it take for its population to double? All right, so again, we're talking about a population, and it's increasing, it's growing, but it's going to be continuous. So we're going to be using this formula again. Let's see, what does it say? New Orleans has steadily won back some of the population it lost in the wake of Hurricane Katrina in 2005. If the current 8.2% annual increase, so that's the rate of increase, 8.2%, which would be 0.082, remains constant, how long will it take for its population to double? So time is the question mark. They don't tell us the beginning population or the ending population. but they tell us they want the population to double. So if it starts out as P, at the end, it would be 2P or double P. Any questions about where I came up with that information? All right, so plugging this all into this formula, we've got 2P equals PE to the 0.082 T power. Well, now we're trying to solve for time, which is part of the exponent. Exponent. A logarithm is an exponent, right? So we need to change this equation into logarithmic form. However, to do that, we can't have anything in front of the exponential part, which is this. So we've got to get rid of this P right there. But we can do that because we can divide both sides by P. We don't know what P is, we don't know what 2P is, but we know it has to be some positive number, because if it was 0, we wouldn't even be talking about the population, and you can't have a negative population. So this gives us 2 equals E to the 0.082 T power. Now we have an equation that is in the form where we can convert it to a logarithmic equation. Okay, so this becomes log base E of 2 equals 0.082 T, changing the exponential equation to a logarithmic equation. However, log base E, that's natural log, so the natural log of 2 equals 0.082 T. Now, to solve for T, we'll divide both sides of the equation by 0.082. So we get T equals the natural log of 2 divided by 0.082. Punch that into the calculator. The natural log of 2, close it up, divided by 0.082. And I get 8.45301439.7. And they rounded to the nearest tenth. It says about 8.5 years. So the 10th, the 5 would round up. We'd get about, so T equals about 8.5 years. Okay. Any questions on that problem? So consider this. Before we punched it into the calculator, we had time as the natural log of 2 divided by 0.082, okay? Where did that 0.082 come from? That was the, in this case, growth rate. And we were trying to double the population, so we had the natural log of 2, which brings us to this general formula. T equals the natural log of 2 over R. If you are dealing with something that is growing continuously, and you want to know how long it's going to take for it to double, rather than using this formula and going through all of this trouble, we can start right here. So the time would be the natural log of 2 divided by the growth rate, which was 0.082. And that will get us our 8.5 years. Okay, let's go back here. Suppose we wanted to triple the problem or triple the population. This would be a 3, 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 this would be a 3. So we'd have the natural log of 3 divided by the growth rate. Or if we wanted to quadruple it, it'd be the natural log of 4 divided by the growth rate. So there's a pattern there, but let's take a look at this shortcut formula and let's apply that to another problem. Now, you can always do it the long way, which would be this, but if you have a population that's growing and you want to know how long it's going to take for it to double, there's your formula. Okay, here it says, how long will it take $1,000 to double? So $1,000 to double if it is invested at an annual rate of 5% compounded continuously. And again, this has to be continuous. So it would be the natural log of 2 divided by 0.05. And the natural log of 2 divided by 0.05, it's 13.86294361. So we'll say about 13.9 years. So almost 14 years. Now, we don't even really need to know the amount of money, okay? If we know it's going to double and we know the growth rate, we can determine the time. Any questions about that problem? All right, let's take a look at one more. This says, tripling money. Find the length of time for $25,000 to triple when it is invested at 6% annual interest compounded continuously. So the time would be the natural log of 3 divided by the growth rate, which is 6%. Natural log of 3 divided by 0.06, and we get approximately 18.3 years. Okay. One of the most common mistakes that students make involves this button and this button. This one being the second function. Students will sometimes have the wrong ideas because natural log is log base e. They confuse that with e to the x. So be very careful that you're using the correct button. Is it a logarithm or is it an exponential? All right. Well, that's all I have for you today. Okay, so we've got these two formulas. For continuous growth. And so I will be back at 1:15 with an office hour. I'm going to go ahead and stop the recording.